Let's hold on a bit. Hold on, let me just admit more. Okay, I think we can start now. So let me share my slide. So hold on, let me share my slide. I believe you can all see the slide. We're starting from where we stopped before. So there are certain errors that are associated with gravimetric analysis. So that's what we're going to look at now in our first lecture today. So we have contaminants or impurities on precipitation. During precipitation, there are some contaminants and the impurities. Sorry about that spelling is impurities. I'll correct it. You can correct it also when I send the slides to you. Okay. So in this case, the precipitates tend to carry impurities from the solution. Impurities are able to go into solution and sometimes precipitate also. So the precipitate of the analytes that we need is also able to, carry some other precipitates that are not what we desire. And so this leads to co-precipitation. Some compounds or analytes or some compounds or so that are able also to go into solution in the mother liquor and also able to precipitate can co-precipitate with our desired analytes. That is one. Then we also have peptidization and we have supersaturation. So we will look at the precipitation errors, the contaminants and impurities in precipitation first before we look at the other two, peptidization and supersaturation. So now the types of co-precipitation that we have from what I just explained to you on the first slide, types of co-precipitation that we can have when we are precipitating our analytes. We have occlusion and inclusion. In our last lecture, I was just about talking about that when we ran out of time. We have surface adsorption, we have isomorphous replacement, and we have post-precipitation. This is under the precipitation or co-precipitation. We will look at peptidization separately and we'll look at supersaturation separately. The number one error is co-precipitation, which we're looking at now. So taking the first one, occlusion or inclusion. Sorry, I need to admit people in. Okay. Taking occlusion and inclusion. Occlusion is a type of co-precipitation in which a soluble impurity or material is enclosed or is entrapped within the crystal structure of the solid. That is, within the crystal structure of the precipitate that were formed, which we are assuming is just our, where we get our analytes, but then other things can co-precipitate. Getting trapped within that crystal structure, that is occlusion. Example, the water with dissolved impurity can be trapped within the crystal. And so this acts as a seat of imperfection within that crystal. So as you can see, the crystal here, and you see the inclusion, what you can see here, the crystal, and then the other co-precipitate that are trapped within the crystal of what we are actually looking for. So generally, occluded substances are distributed in a non-homogeneous or uneven fashion throughout the crystal. You can even see the crystal, how it is. It's not homogeneously distributed, it's just in an uneven fashion. That is how you see the occluded substances inside the crystal of the precipitate that we're looking for. Let me admit some people in. Okay. So, in addition, amount of occluded substance is greatly influenced by certain conditions. I still need to admit people. Distractions. So the amount of occluded substances that you have in your crystal is greatly influenced by certain conditions and the manner of formation of the precipitate, which we're going to see here. So in many cases, you see the hole is formed, hole within with the solvent containing dissolved impurity. You may have holes included, trapped in the crystal, and then that hole contains the solvent that is carrying the impurity and is trapped inside there. So that is that with occlusion. Then inclusion occurs when impurities occupy a lattice site in the crystal. A lattice site in the crystal, where the crystal, just as the crystal is forming, that one also, the ions of the impurities also taking its place, proper place inside the crystal, as if it's just part of the proper thing. That is the inclusion. So when the ions or impurities of the same size or charge are trapped within the crystal lattice, so it's just as if it's the same crystal that is formed. Because of the same size, because of the same charge, they are trapped, and actually is not the analyte we're looking for. It's the impurity, because it has the same size of ion, the same charge, almost the same, and so it just behaves as if it's our analyte. So that's another way of co-precipitation, which is called inclusion. Okay, so difference between inclusion and occlusion. I will need you to know that. You close from lecture today, go and look at it, that's your class activity, check very well the difference between occlusion and inclusion. Okay. So here, occlusion and inclusion impurities are difficult to remove. They're very difficult to remove. They cannot be removed by washing. Inclusion is not common. The occlusion is much more common. But, you know, it may be corrected by removing the ion prior to precipitation. Before the precipitation occurs, you know the ions that are not supposed to be, that you're not looking for. So you try, that is not your analyte, but you know it's going to be in that medium in your solution. So you remove such ions first before you go ahead with your precipitation. That is how you can handle it. It cannot easily be removed by washing. Okay. So occlusion can be removed by dissolving and then re-precipitating the precipitate. You dissolve it again, you've gotten the precipitate, and then you suspect impurities. Perhaps you weigh it and you weigh it and you see it's bigger than what you're supposed to have. It is heavier, is much more concentrated than what you're supposed to have. So you know there are definitely impurities there. So you go and redissolve it and then precipitate it. And in the process, you can decide to so and so ions must have been trapped in there, and you see how you remove those ions, and then that are not the analyte you're looking for, and then you now precipitate. So that is it. And I'm still admitting your colleagues. So digestion is also an effective method of reducing the quantity of entrapped contaminant, in this case, inclusion. So you can reduce the quantity of contaminants that enter into your precipitate by inclusion. You can reduce it using digestion. I've explained to you what digestion is all about before. Okay. So I've mentioned inclusion is difficult to remove. Impurities by inclusion and occlusion, they're difficult to remove. Then I told you how to remove them. So, sorry. Okay. So I think I've skipped a slide. Sorry. Okay. So, surface adsorption is what we want to look at now. We have looked at, under the co-precipitation, we have looked at A, which we looked at as A is occlusion and inclusion. B, surface adsorption, is what we're looking at now. Sorry. I'm distracted by some people coming in for admission. So adsorption, surface adsorption, is common for all precipitate, but significant in precipitates with large surface areas. It's common in all precipitation. It is much more significant in precipitates that have large surface areas. I'm still admitting your colleagues, so sorry. That's the great distraction for me. And it's slowing us down. Okay. So excess electrolytes and other impurities get adsorbed on the precipitate surface. They are adsorbed in the form of primary adsorbed layer and counter layer. I talked about primary adsorbed layer and counter layers before in the previous lecture, but we're still going to talk about it today. I'm going to explain it better to you in this lecture. So it may be minimized by digestion or washing. It's difficult to remove it from colloidal precipitates. It's difficult to remove, adsorb the precipitates that are adsorbed on top of precipitate. It's difficult to remove the contaminants that are adsorbed on top of the precipitate by washing, from colloidal precipitates. I have so much distractions here. Admitting your colleagues, too much distraction. Okay. So, we're looking at an example now to make it clearer to you. If we're looking at silver chloride as an example, let's see the primary adsorption layer, what happens there, and we'll also see the counter ion layer, what happens there. We're using silver chloride as an example. So the ion in excess adsorbs on the surface of the precipitate. Ion that is in excess, let's say that silver ion is in excess. That is what we now stay at the surface of the precipitate of silver chloride that is formed. So if it is chloride that is in excess, then that one is going to be there at the surface. So on the other side, let's see the counter ion layer. The charged crystal attracts ions of opposite charge. If it is, well, let's go on. So ions of opposite charge attract the opposite one. So what is on the surface will attract another opposite ion that is inside that system. For example, you have nitrate attracted to positive crystal, result in a layer of silver nitrate around the silver chloride. So it means what you have, you now end up having an impurity of silver nitrate on top of the silver chloride that you have. So let's say that you have sodium ion there at the surface. Sodium ion attracted to negative crystal results in sodium chloride around your silver chloride precipitate. So you now have sodium chloride there as impurity on it. So that is it. So the ions itself, whichever one is in excess, will be on the top, and it will attract the negative one, or whichever one will attract the opposite one and form a different compound completely on top of the layer of your precipitate of your analytes that you required. And so that makes it contaminant on your analytes. This is what I'm talking of. I showed this to you before. So in this case, if you have more of the nitrate at the primary layer up there, So, or let me use the silver there. Is there the nitrate? You have more of the nitrate and you have your silver there. So the nitrate there will be attracted to the silver and to form silver nitrate, which is not what you're actually looking for. We're looking for silver chloride that you're seeing there in the middle that is already formed. So now silver nitrate will now deposit on top of the layer that you're actually looking for. So that's the explanation to that. Let me just still admit your colleagues, please. Okay. So now then another one is isomorphous replacement. Still under co-precipitation, isomorphous replacement. So two compounds are said to be isomorphous if one, they have the same type of formula, two, they crystallize in same geometric forms. So when their lattice dimensions are about the same, one ion can replace another in a crystal, resulting in a mixed crystal. Replace the other one and it looks like if it is what's supposed to be there and something else is replacing it because they have almost the same size and they form crystal in the same geometrical way. So this process is called isomorphous replacements. I will give you an example here. In the precipitation of magnesium ion as magnesium ammonium phosphate, potassium ion has nearly the same ionic size as ammonium ion, and so can be replaced to form magnesium potassium phosphate instead of magnesium ammonium phosphate that you are trying to form. So isomorphous replacement is very serious and very little can be done to remove it. Sorry, let me admit some more people here. Okay. So we have post-precipitation. That's another form of co-precipitation. Post-precipitation. Okay. So this is when impurities precipitate out of the solution into precipitate desired. That is, you've already formed your precipitate. Your precipitate is already formed, but in the solution where your precipitate is, there are some impurities there. So after forming your precipitate, those impurities now form on top of the precipitate. They now form on top of the precipitate. So this can be prevented by filtering the precipitate after the desired precipitate is formed and corrected by dissolving and reprecipitating the precipitate. So we now go to the number 2 error. The first error we saw, co-precipitation, which we have looked at the 4 different types of co-precipitation. The second error in gravimetry is peptization, which is a redissolution of coagulated colloids by washing and removing inert electrolytes. So in the so by coagulation and agglomeration, the suspended colloidal particles, they coalesce to form larger filtrable particles. These larger filtrable particles are, inert electrolyte, which allows closer approach. So then this inert electrolyte just allows the same approach like resolution and coagulating back, coagulation, agglomeration, and so on. So the inert electrolytes also allow a situation that is just like this, in this same approach. And so peptidization reverses it, leading to error. Peptidization releases it by redissolution of the coagulated colloids. And so this leads to error. And then you have supersaturation, number 3 error. The first one is co-precipitation. The second one is peptidization. And the third one is supersaturation. A supersaturated solution is a one that contains greater concentration of solute than expected at equilibrium. I believe you can remember your CHM 121, which we took time to teach you on supersaturated solutions. So a supersaturated solution produces precipitates, which are colloidal in nature. And remember, in the last lecture, I've told you that colloidal precipitates are very difficult to filter. So to avoid supersaturation, these are the things that need to be done. Reagents should be added slowly with constant stirring. Precipitation should be carried out at high temperature. Precipitation should be from homogeneous solutions. Precipitation from homogeneous solution is what we call also kinetically controlled precipitation, which I'm going to explain to you further in some few slides from here. Allow me, please. I still have some people to admit. Okay. So you have your class activity. Go back home and look at them. List the common errors in precipitation. Gravimetry.
Thank you, sir. God bless you, sir. Thank you, sir.
Who are the person that are making noise? Please mute yourselves. Okay, your class activity. List the common errors in precipitation gravimetry and also state how to reduce or correct them. This is just what I just finished showing you. So you should know how to do that. Go back and read through it so you understand it better. Now, the precipitation from homogeneous solution that I was just mentioning in the last slide is, I will shorten it to PFHS. It's otherwise called kinetically controlled precipitation. It's a technique that used to overcome the problem of the usual precipitation errors. Advantages are: 1, undesirable concentration effects are avoided, like all those co-precipitation and all those things. So the precipitate form is dense, more readily filtered, and easily washed. Another advantage is that the precipitate formed exhibits minimal co-precipitation, does not normally require a further purification or re-precipitation operation. So when you carry out PFH is precipitation. Let me admit some people, please. Okay. So in this kind of precipitation, precipitates occur on the precipitate nuclei. Precipitation builds up on the precipitate nuclei, like the lecture I gave to you maybe 2 lectures ago. The number of heterogeneous sites does not depend upon the concentrations of solutions. And the concentration is generally small in any step. So it means that you might have some heterogeneous sites there, but the sites will be just few. And so it's not going to be a problem. Also, the precipitating solution is not added as in conventional precipitation. So not like you just add the solution directly like that. In this case, you add it very slowly by homogeneous chemical reaction within the solution to generate homogeneous chemical reaction. So you add the precipitant slowly. Then this eliminates the undesired effect of concentration that are associated with conventional precipitation. So PFHS reduces co-precipitation. I've already talked about that. And then you can achieve PFHS by change in pH, controlling ion release, like hydrolysis, then reagent synthesis, and then precipitation from mixed solvents. You can use this approach, these approaches to achieve PFHS. There are disadvantages also of PFHS. One is that it is not rapid, it is slow. It can now be seen that if von Weymann's rules, remember von Weymann's rules that I told you in I think this last lecture, if you have to strictly adhere to von Weymann's rule, the nucleation process is restricted to heterogeneous sites, resulting in the formation of pure and large crystals. There are certain practical limitations which discourage strict adherence to von Weymann's rule. So to overcome that, we use PFSH. So sorry, let me admit, see, have a lot of people here waiting to be admitted. Okay. So we see examples of PFHS processes. I don't know, people are just coming in now. Hold on, let me admit them. So I'm so distracted because of people coming in. Okay. Example here is in the production of hydroxides and basic salts. For instance, urea is used in the control of pH hydrolysis of urea. Urea is used in the control of pH hydrolysis of urea. So here you have the hydrolysis of urea, which gives you ammonia and carbon dioxide. Urea itself has negligible basic properties, but disintegrates to give ammonia, which is basic. So the rate of hydrolysis can be controlled by heating to increase the rate or by cooling at a desired pH. So using this approach, This same approach that is used for urea, using this same approach, we can precipitate aluminum produced in the presence of specific anions. I will give you some examples here. Sorry, I have to admit other people in. Okay, I'll give you some examples. So here you have urea hydrolysis. This method can be applied to precipitation of barium chromate in the presence of ammonium sulfate. This same method of urea hydrolysis can be used in the precipitation of aluminum as chromate. Can also be used for phosphates. Insoluble phosphates can be derived from trimethyl phosphate by stepwise hydrolysis. Then metal phosphates may also be used. You can also use it for oxalate. Here the pH of the acid may be raised, leading to slow formation of oxalate ions. So you have some class activities. What is precipitation from homogeneous solution? What is precipitation from homogeneous solution? It's the same thing as PFHS. What is PFHS? So you go and look at it very well. It's what I just completed in the last slide. So now let's see calculations. Percentage analytes in the sample is equal to the mass of analytes divided by the mass of the sample multiplied by 100. Remember in our 2 lectures back that we talked of using stoichiometry when you're carrying out your analysis. The ratio of the reactants to the product. So you're going to see it here. It's going to be used here. Hold on, let me admit some people. Okay. So the mass of analyte from sample divided by the mass of the precipitate is equal to the formula weight of analyte divided by the formula weight of the precipitate multiplied by the mole of the analyte over the mole of the precipitate. So, sorry, let me admit some more people here. Okay. So this is the appropriate ratio of the formula weight of a substance salt, that is for your analyte, to that of the substance weight. Gravimetric factor is what we can easily use. So if you calculate your gravimetric factor, you can just multiply the other ratio by your gravimetric factor. So how do we get gravimetric factor? It's the mass of analyte from sample divided by the mass of the precipitate. Then this equals to the weight of the substance divided by that of the substance weight. I've mentioned to you the formula weight is what I mean. The formula weight of the substance. So, okay. Then you multiply it by the ratio of the mole of what you have over, or the mole of your analyte by the mole of the entire precipitate. And it's okay. Now, the initial formula I gave you in the very first lecture captures everything, including the gravimetric factor and everything inclusive. So, but here, trying to show you how you can calculate by just calculating your gravimetric factor and multiplying it by the mass of analytes in the sample over the mass of precipitate. So, example here is silver chloride. If this is your precipitate, and then you're determining your chloride in silver chloride. So, mass of analytes from sample divided by mass of the precipitate here is same as mass of your chloride divided by mass of your silver chloride. And this is same thing as your gravimetric factor. Then you now multiply your gravimetric factor by the mole ratio. So therefore, the mass of analyte is mass of precipitate multiplied by gravimetric factor. So mass of chlorine ion is mass of silver chloride multiplied by gravimetric factor, which is equal to mass of silver chloride times the the formula weight of chlorine divided by the formula weight of silver chloride. So I think if you can look at the first paragraph up there, it is clear. It's very clear, no need of too much details again. But what is down here is the same as what we have in the first paragraph there. So that should be easy. Just please hold on. Let me admit some more people. Okay. So now look at this table, how to generate your gravimetric factor. For analytes like chloride ion, and which is in the precipitate of silver chloride, the formula weight of chloride divided by formula weight of silver chloride is your gravimetric factor. So this is how you use the different analytes in the different precipitates here, and you can calculate your gravimetric factor here. So, because you remember, you can now use your gravimetric factor to multiply by by the ratio that you have in your stoichiometry. So you can now use your gravimetric factor here to multiply and get your analyte. Okay, so a recap now is errors in gravimetric analysis. What we have looked at, and then precipitation from PFHS. Please give me one. Please give me 1 minute, please. So you can go back and look at this. We just finished this. When you go home, take time and look at these errors and then the PFHS. You have an assignment here, which is already solved here. And just give me some time again. I have to admit people. Okay. You have an assignment here, which is already solved here. So at the end of today's lecture, I'm going to give you your notes. So you go back and do the exercise, see how you can solve this assignment, but I already have given you solution, which you're going to look at. So you just go back and practice those solutions and see how you can do it. But it's very simple. So orthophosphate is determined as ammonium phosphomolybdate. This is an example. So calculate the percentage phosphorus and percentage phosphorus pentoxide if the precipitate from 0.2711 gram sample weighed 1.1682 grams. That's the question, and we're going to solve it. Permit me to admit some more people here. I think network is just sending them out and bringing them back in. Okay, so now this is the answer. So this is how you can solve it. You get the gravimetric factor. Now you get the mass of the analyte over the mass of the precipitate. And then you multiply that by your gravimetric factor. And then you now get it in percentage by multiplying it by 100. So that is how you do this calculation, and then you will get percentage of the analytes in your sample as from that question. Okay, so this is it, and for the phosphorus and also for the phosphorus pentoxide. So you do this, the same thing you did for the first one, you do the same thing for this one. So if I give you this also as an just what to do, it's already here. I've already given it to you, but it's just for you to go and practice it properly. You have analytes here I give to you. I also give you the precipitate, and I want you to give me the gravimetric factor. You know how to calculate the gravimetric factor. So you use the particular analytes that I'm asking you, and then the particular precipitate, calculate the gravimetric factor. So this is something that you can be given in the exam. So go back to the table I gave you, the table here, and see how you do it, and then go to your formula and see how you can calculate your gravimetric factor, which is the formula weight of what we're looking for, the analyte over the formula weight of the overall precipitate. So you go and do that, rehearse, practice it, so you will not have to complain in exam hall. This is another example. 0.3516 grams. It's supposed to be a classwork. Well, from this question, I also have solutions for you. So 0.3516 gram sample of commercial phosphate detergent was ignited at red heat to destroy the organic matter. The residue was then taken up in hot HCl, which converted phosphorus to this phosphate, and then the phosphate was precipitated with magnesium ion followed by aqueous ammonia to form magnesium ammonium phosphate. And after being filtered and washed, the precipitate was converted to magnesium phosphate by ignition. The residue weight was 0.2161 gram. So now calculate the percentage phosphorus in that sample. So there's an answer here also for you. Get your gravimetric factor, just like what we did in the first example. You just do the calculation. So I have some more classwork here for you. We're almost at the end of the lecture. So go and see how you can solve these problems. It's just exactly as what we have done. The other two examples have shown to you. It's just exactly that way. I don't know why somebody is just coming in at the end of the lecture. So this is an assignment for you. Go and try it and calculate them, all these two questions. Solve these problems, and then let's know if you had any issue. So this is the end of this lecture. So this is the end of the gravimetric lecture. At the end of this lecture, I'm going to give you the notes, and I'm going to send to you also the YouTube link so you can watch that one and also have your notes. So we've come to the end of the lecture today. And thank you. Let me just stop sharing. And I don't know if anybody has any question. So I'm going to send the link to the YouTube lecture to you. And then I'll also send the lecture, the slides to your class rep. So you can go through them, solve those questions, solve those problems. And then the next lecture will be a different topic. All right. So I'm bringing the lecture to a close now.